Synthesis of Aplysia secosterol A. It is a 9,11 secosteroid isolated from the CA Aplysia coridae, which is shown here on the right side, and it is notable for its unique structural features and potential biological activities, making it significant in natural products and pharmaceutical research. The article is written here in Royal Society of Chemistry format. Retrosynthetic scheme. This is the structure of Aplysia secosterol A, and if we open this ring up, we get this structure. And if we break this carbon-carbon double bond, we get these two fragments. And for this video, I'm going to focus on this fragment. I'm going to talk about palladium catalyzed Suzuki reaction that made a new carbon-carbon bond between these two carbons, and enolate alkylation, which formed a new carbon-carbon bond between this and this carbon. A hydroboration oxidation reaction using 9-BBN, which introduced hydroxyl group onto this carbon. First reaction is enolate alkylation, where a new carbon-carbon bond is formed here. I'm going to refer to some of the R groups as shown here. In the mechanism, in the first step, the aldehyde, which is a strong bulky base, is going to selectively deprotonate this alpha hydrogen. And this selectivity arises because this alpha hydrogen is quite acidic due to the electron withdrawing nature of the carbonyl group next to it. And this regioselectivity ensures that the carbon-carbon bond forms at the alpha position of the original carbonyl compound. And this deprotonation leads to the formation of an enolate intermediate, which is stabilized by the resonance, where the negative charge is delocalized between the oxygen and the alpha carbon. In the next step, as into alkylation, the enolate acts as a nucleophile and attacks an electrophilic carbon of this allyl iodide, displacing the iodide ion via SN2 mechanism. Since the enolate intermediate is planar, the nucleophilic attack can happen from either the top phase or the bottom phase. However, the steric hindrance from the substituents such as phenol, hydroxyl, methyl, and all of these groups, this will favor the top phase of the enolate. This selectivity leads to the formation of a specific stereoisomer as shown by the wedge at the new carbon-carbon bond. In the second hydroboration oxidation reaction, an alkane is converted to an anti-Markovnikov alcohol product. In the first step, 9-BBN reacts with an alkane to form an organoborane. 9-BBN is sterically hindered borane, meaning it adds to the least hindered carbon of the alkane, and this ensures regioselectivity, where the boron adds to the least substituted carbon of the alkane and the hydrogen adds to the most substituted carbon. Additionally, hydroboration is a syn addition, meaning that both boron and hydrogen adds to the same phase of the alkene, resulting in a cis configuration of boron and hydrogen. In the step 2, hydroxide ion from sodium hydroxide deprotonates hydrogen peroxide that forms hydroperoxide anion. This hydroperoxide anion acts as a nucleophile and attacks the boron of an organoborane, and a negative charge from the oxygen transfers to the boron. A 1-2 shift occurs where the carbon-boron bond migrates onto oxygen and hydroxide ion leaves. In the next step, hydroxide ion attacks boron and forms an oxyanion. This oxyanion reacts with the water, protonating the oxygen, and forms the alcohol product. In the final palladium catalyzed Suzuki reaction, a new carbon-carbon bond forms. Palladium catalyst is in +2 oxidation state and needs to be reduced to 0. Transmetallation reaction, an allyl boronic acid is activated by sodium hydroxide, and it transfers this allyl group onto the palladium center. In the next reductive elimination step, these two allyl groups couple together and leave, and palladium catalyst gets reduced from +2 to +0 oxidation state, which can enter the catalytic cycle. For the catalytic cycle, I'm going to refer to R prime group as shown here. The cycle begins when the palladium 0 species reacts with an organic halide, which is acting as an electrophile. The palladium inserts itself into the carbon halide bond, forming a palladium 2 complex. This step is called oxidative addition, and the oxidation state of palladium increases by 2 and the coordination number increases by 2 as well. Next step is ligand exchange, where the iodide ion is replaced by the hydroxide ion. This prepares palladium complex for the next step by making it more reactive. Next, the boronic acid, which is acting as a nucleophile, undergoes transmetallation with the palladium 2 complex. In this step, the alkyl group from the boronic acid replaces the hydroxide on the palladium complex. This is the key step where the two coupling partners come together. Importantly, the palladium complex adopts its cis configuration during this step where the two organic ligands are positioned next to each other. This arrangement is crucial for the next step. In the final step, palladium-2 alkyl complex undergoes reductive elimination. The two ligands on the palladium couple to form the new carbon-carbon bond, while regenerating the active palladium catalyst that can re-enter another catalytic cycle.